Hello, welcome to this video lesson. It's on nucleophilic substitution. So let's work out what nucleophilic substitution is. Well, it's a reaction mechanism, and we are obliged to study two different types of mechanism. One is this, substitution, and another one is elimination, which we'll deal with later. Okay, so substitution is a reaction mechanism. What's a mechanism? Well, a mechanism, like we were introduced to before, just lists out the steps that are involved in the reaction. So reactions don't go straight from reactants to products usually. Usually there's a few steps involved, and those steps are called the mechanism. And so we're going to study the mechanism, which is nucleophilic substitution, for halogenoalkanes. So we need to understand the reactions of halogenoalkanes and how they react with nucleophiles is this nucleophilic substitution reaction mechanism, an example of which is here. So our nucleophile is our hydroxide ion, our halogenoalkane is here, so we've got bromoethane here, and you can see we've got this, this bromine is substituted out and replaced by the hydroxyl group that came from the hydroxide ion, and the bromine atom leaves as a bromide ion. And so that's an example which we're going to study in more detail on the following slides. So let's have a look at this general reaction mechanism for nucleophilic substitution reactions. So we can start off with a generic halogenoalkane. So the alkane part is going to be CH3CH2, and the halogen we're going to denote by X, so it could be fluorine, chlorine, bromine or iodine. And we're going to react that with a generic nucleophile, and so we're going to call that Nu for nucleo, give it a minus charge, and that's going to make the CH3CH2 alkane part of the new molecule, and the nucleophile is going to add on to the end of that because it substituted out the halogen, which leaves as an ion, or a halide ion. So notice that the charge is balanced on each side of that equation. We have a -1 charge here on the nucleophile, and we have a -1 charge here on the halide. So they balance as they have to in a correctly drawn equation. Okay, so let's have a look at the steps. So first of all, we're going to draw this displayed formula of the halogenoalkane. So we've got two carbons, the methyl group on one end, CH2 group, and we've got the halogen on the end of that molecule. So the first thing to say is that the electrons will be drawn towards the halogen because the halogen is more electronegative, and so that will give the halogen delta minus charge, and it will give the carbon the delta positive charge. So then we can include the nucleophile. So Nu minus is our nucleophile, but we need to draw our lone pair because our curly arrows go from lone pairs to atoms. And the first step is to draw a curly arrow from the lone pair of the nucleophile to the slightly positive carbon atom. So we're going to draw a curved arrow like that. Coming from the lone pair, that's an important point. It has to be from the lone pair and has to point towards the positive carbon ion. So then what happens is we get a new bond formed. All right, so that lone pair forms a covalent bond with that carbon atom. So let's draw that out. The methyl group is just the same, and the CH2 group is just the same, and we now have the nucleophile included. So in red, let me circle these two electrons on the nucleophile, just to make clear that they are the two electrons making this new covalent bond. But at the same time as this new bond forms, then the electrons, let's draw the electrons in green on the carbon halogen bond. The electrons in that bond go from the bond to the atom, to the halogen atom, like so. So we've drawn another curly arrow from the bond to the halogen atom, and so then we get this molecule here. Draw our methyl group as before, draw our CH2 group as before, and carbon of course can only have 4 bonds, and it is preferring this new bond to the nucleophile, and we have left with X minus. So the X has both of those green electrons, which gives it, one of which was its original electron that it contributed to the covalent bond, and one of those green electrons was the carbon's electron, and it's left with both of those electrons. So that gives it that, let's draw it in green, that gives it that extra electron, which gives it the negative charge there. Okay, so that is the general nucleophilic substitution reaction using X for halogen and Nu minus for the halogen, for the nucleophile. So what we'll do now is we'll look at 3 types of reaction to make 3 different types of product. So we can make alcohols in this way with this nucleophilic substitution mechanism. Alcohols. We can make alcohols. All right. We can also make nitriles by starting with halogen alkanes, and as well as alcohols and nitriles. We can also make amines. So we can start from halogen alkanes, and we can make either alcohols, nitriles, and amines depending on what nucleophile we choose. So I guess you can guess what nucleophiles will be used. The hydroxide nucleophile will be used to make an alcohol. The cyanide ion will be used to make nitrile, and the ammonia molecule will be used to make amines. So we're going to, it's the same mechanism each time as this general one, but we're going to go through each mechanism individually in any case. So firstly, let's make some alcohols with the hydroxide nucleophile, and let's write out the general equation. So R is just an alkyl group, and we've got X, which is the halide, so that's our halogeno alkane, and we're going to add the hydroxide ion, and we're going to end up with ROH, which is our alcohol, and we're going to substitute out the halide ion like so. So that's our general reaction. Let's do a specific example, starting off with bromoethane. So ethane is going to have 2 carbons. There's 2 carbons. Let's draw our hydrogens in for completeness. And if it's bromoethane, we're going to have bromine on the end like so. And the first thing that happens that we'll draw in red is that our bromine is going to get delta minus, and our carbon is going to get delta plus, because of the differences in electronegativities between bromine and carbon. Then our nucleophile, which we remember to draw our lone pair in, is going to attack that positive charge. So we draw our curly arrow from the lone pair to the slightly positive carbon ion, and then we're just going to do this step in. So the next step we're going to do in one go. So that carbon that was slightly positive can only have 4 bonds. So at the same time as the nucleophile forms a new bond with that slightly positive carbon, these electrons in this bond, let's draw them in red, these electrons in this bond, they are going to move on to the bromine atom, in which case the bromine atom leaves and the hydroxide ion joins with the carbon atom. So we're going to draw our new molecule like this. Methyl group, CH2 group, and instead of our bromine we've got a hydroxyl group, which is now neutral because the extra electron left with the bromine. Now the bromine has got that extra electron, both electrons in the covalent bond went with the bromine, giving it a full 8 electrons, and we can draw one of the lone pairs there like that on the bromine. So that's how we make an alcohol, because this is our alcohol. So that's going to be ethanol, which we made from bromoethane and hydroxide. So next, let's make some nitriles with cyanide and halogen alkanes. But as we do so, let's just get our heads around what cyanide and nitrile molecules look like. So start off with cyanide. Let's have a look at hydrogen cyanide. So hydrogen cyanide is a molecule that looks like this. If we just draw the displayed formula, we've got a hydrogen and a nitrile group. So that looks like that with a triple bond between the carbon and the nitrogen. We can make that into potassium cyanide by reacting it, for example, with potassium hydroxide. So we would get potassium cyanide, which would be ionic. K+ would exist in aqueous solution with a cyanide ion, like so, with a triple bond again between the carbon and the nitrogen. So that's a look at a couple of cyanide molecules, ions, in the case of potassium cyanide. Let's have a look at ethane nitrile. Okay, so we're going to have a look at a nitrile. Let's look at ethane nitrile. Ethane nitrile. Ethane is going to have 2 carbons. So the one carbon is going to come from the halogen alkane, and the other carbon is going to come from the cyanide ion. So would look like so. Ethane nitrile would look like so. So why don't we go ahead and make some? What should we make? We're going to make propane nitrile. So propane nitrile is prop is going to have 3 carbons. So it's going to make this 1, 2, 3. The third carbon there, the one I've just drawn, will come from the cyanide ion, and the first 2 will come from the halogen alkane. So I'm drawing the product first this time, in case you were wondering what I was doing over this side of the page. So because what we want to do is we want to make propane nitrile. Propane nitrile, which is so. Now, what are the steps to make that? Well, we want to start with a halogen alkane that has 2 carbons in it. So that is going to be, let's start with bromoethane. Right, so there's our bromo. There's our 2 carbons. Single bonds to hydrogens makes it the alkane. So that's bromoethane. Bromoethane. And our nucleophile that we're going to use is going to be the cyanide ion from potassium cyanide. But let's do the mechanism. So that is going to become delta minus, and that is going to become delta positive because of the difference in electronegativities. And then when our cyanide ion with its lone pair my pen doesn't like drawing lone pairs for some reason, with its lone pair and its minus charge, that lone pair is going to attract with a curly arrow. I'm just trying to make that a little bit curly to show it's the movement of electrons. That is going to attack that slightly positive carbon ion, forming a new bond, a new covalent bond, using those 2 electrons in the lone pair. And simultaneously then what happens is that the carbon-bromine bond breaks with the 2 electrons going from the bond. So you draw the curly arrow going from the middle of the bond to the bromine atom, like that, in the second step of the reaction. And that it gives us the product that we've already drawn, but we also have to complete the equation by giving our bromide ion as the other product, like so. Now that all happens, but to make it happen, you do need to give it a bit of encouragement, and that encouragement comes in the form of a reflux reaction in the presence of ethanol. So refluxing is when you heat the reaction mixture, and to save losing your volatile reactants before they can react, you attach a condenser to the top of the reaction vessel so that any vapors that come off because you're heating it will condense and drip back down into the reaction mechanism, giving them a good chance to react. So they're the reaction conditions you need to make that reaction happen. And if you do so, you can make some propan-nitrile. And so that's the second group of products we can make with our nucleophilic substitution mechanism. And we'll move on now to the third type, which is we're going to make some amines. So in order to make some amines, we're going to start off with a nucleophile ammonia, and I think we're familiar with ammonia, but let's draw it out. So ammonia NH3, so you're going to have 3 hydrogen bonds, 3 bonds to hydrogen atoms, but nitrogen, as you know, is in group 5, so it's got 5 outer electrons, 3 of which are involved in those 3 bonds there, 2 are left over and are a lone pair. So they're a lone pair of electrons, which is handy because that's what a nucleophile needs to go and attack something positive. So let's deal with amines now. What's an amine? An amine is a molecule with an NH2 group. So let's have a look at a couple of examples. Let's have a look at methyl amine. So methyl amine is going to have 1 carbon and an NH2 group. So we're going to draw it like so. So that's methyl amine. And ethyl amine would, so let's draw ethyl amine as well. Ethyl amine, because I want to just highlight the fact that the nitrogen in the amine group has a lone pair. Right, so ethyl amine is going to have 2 carbons, like so. This time I'm going to draw the hydrogens at right angles like this, because the nitrogen atom there has 3 bonds, as you can see, so it's got another 2 electrons that we want to take account of, that we're going to draw like so. And the reason why I'm being particular about those 2 electrons, that lone pair, will become clear in a second. So this nucleophilic substitution reaction is slightly different to the other 2 that we've done. It's got an extra step to it. So what we're going to do is we're going to start with our bromoethane again. So bromoethane, 2 carbons, like so, surrounded by our single bonds to hydrogens, and our bromine there, and as we have done before, first step is the same as before. We've got delta minus, delta positive, but in this case we have the nitrile ammonia, so we're going to draw our ammonia molecule like this, because we have to make the lone pair on the nitrogen very clear. So that's our lone pair on the nitrogen, and it's that lone pair that attacks our positive carbon atom, and as it does so, it forms that new bond. But carbon can only have 4 bonds, so the bond between the carbon and the bromine breaks, and the 2 electrons that are in that bond go to the bromine atom, as we have drawn with that curly arrow there. So that whole process needs to go on in the presence of ethanol, and that creates this molecule here. So let's just make sure we've got our lone pair in there on our ammonia. So let's draw the molecule formed, and this is interesting and slightly different because we have a charge remaining on the nitrogen. Okay, so this part of the alkane part of our molecule is just the same. Now we have added a NH3 group to the end of the alkane, and that nitrogen is going to be positive. Right, so that nitrogen is going to be positive. Let's make sure we understand why. By drawing in the 2 electrons that were in that bond there. So they were the 2 electrons in the carbon-bromine bond, and they left, right, to go with the bromide ion that left. So let's draw that lone pair. So those 2 red electrons have both left with the bromine atom, making a bromide ion, and so that carbon is 1 short of electron, but the positive charge finds its way over to the nitrogen atom in that molecule, that intermediary molecule. And so nitrogen, as well as being positive, is also quite electronegative, more electronegative than the hydrogen. So this hydrogen becomes delta positive, and this is delta. No, let's not do it like that. Let's just leave it like that. So we have an unstable situation there with that positive ion. But of course, what we do have is other ammonia molecules floating around in solution. Let's draw one. So we're going to draw an ammonia molecule like this with the lone pair, and that lone pair is going to grab this hydrogen, right? Because that hydrogen is going to have electrons drawn away from it by the positive nitrogen atom, and that lone pair is going to be attracted to it. And so what you then get is, let's draw it down here, what you then get is a new molecule, of which again the alkane part is all unaffected, blissfully unaware of all this stuff that's going on at the other end of the molecule. So we've still got our nitrogen, we've still got the hydrogen there and the hydrogen there, but the other hydrogen has left, but it's left without the electrons, and the 2 electrons as a lone pair stay on that nitrogen there, and let's just circle them in red like that and highlight that they were these 2 electrons in this covalent bond there, and that's where they become. So this hydrogen atom here has left just as a proton, hasn't it? and so the other product that we get is that this second ammonia molecule plus that hydrogen, that proton, that hydrogen ion that comes off, and that makes an ammonium ion, like this. So we've got our nitrogen, we've got our hydrogen, right? So that was what was the second ammonia molecule, and this hydrogen that I'm drawing now is the hydrogen that was on the intermediary ion, and that all has a positive charge, and we draw the positive charge on the nitrogen, like so. And so there we have our two products, which, in fact, yes, you could call it two products. You've got your bromide ion, you've got your ammonium ion, so we could call that ammonium bromide, and you also have your ethylamine, which is this molecule here. Ethylamine. And of course we had our ammonium bromide. So lastly, we're going to talk about the reactivity of halogen alkanes and the trend that exists depending on the halogen. So let's be clear that about what we're comparing. Let's say we're comparing fluoromethane, fluoromethane, and instead of the fluorine, we could compare that with chlorine. Instead of the chlorine, we could compare that with bromine, and instead of the bromine, we could compare that with iodine. So there would be 1, 2, 3, 4 different halogen alkanes with different halogens on the same alkane. So there we're comparing the reactivity of, and let's define reactivity in this situation as well. So speed of substitution. So speed of substitution. So that's what we're talking about. So if fluoromethane is substituted quicker than chloromethane, then that would be your comparative reactivity. So let's imagine what two factors could affect it. So let's draw fluoromethane out, like so. You're going to have a very polarized carbon-fluorine bond, aren't you? So those two electrons are going to gravitate very much towards the fluorine, and you're going to have quite a big delta positive on your carbon atom, because fluorine has grabbed most of those two electrons. In which case, that delta positive carbon atom would be very attractive to the nucleophile. All right. So one. Whereas let's take bromo. Let's do bromo. Yeah. So let's do bromomethane. Okay. So this bond is less polarized. Let's draw that dotted, and just illustrate that by doing a little tiny delta minus and a little tiny delta plus, like so. So the carbon atom is slightly less attractive to a nucleophile. So if there was a nucleophile here with its lone pair, so it was a hydroxide ion, is it going to attack that one, or is it going to attack that carbon there? Well, clearly it's going to go and attack this one, everything else being equal. All right, so that factor alone, which we'll call the polarity of the bond, so the polarity of the bond, would favour the fluoroalkanes. But there is another factor, and the other factor is the strength of the bond, the carbon halogen bond. All right, so let's put a number 1 there, because that's the first factor that affects the speed of substitution. The second factor, which is the strength of the carbon halogen bond would also, obviously, if it's a weak bond, it's going to substitute more quickly than if it's a strong bond. So let's have a look at the bond enthalpies of those carbon halogen bonds. Here we have a chart here. So our carbon fluorine bond, if this is our bond enthalpy on the y-axis, so this is the strongest bond, and our carbo-bromo bond and carboiodide bond is our weakest. The weakest bonds. So this weakest bond here and here, they are going to promote fast substitution. Fast substitution when the bond is weak, and that counteracts the polarity of the bond. So the polarity of the carbon-fluorine bond would suggest that it has been more attractive to the nucleophile. But the fact is that the second factor, the strength of the bond, is the most important factor. Most important factor. Right. So the trend in reactivity, or the speed of substitution of halogen alkanes, is fastest with the bromo alkanes. All right. So let's write that down. Fastest substitution bromo alkanes. Last thing to say would be just to explain why the strength of the carbon halogen bond is weaker with the bigger halogens, and it is exactly that is the size of the halogen that weakens the bond. So carbon is quite a small atom, whereas bromine and iodine very big atoms, and that size differential weakens the bond, and therefore makes the halogen alkane easier to substitute nucleophiles onto than with the fluoroalkanes or chloroalkanes. Okay, so that's it for this video lesson. I hope that's all been clear. Any questions, please put them on Classroom.